So part two of this magnetism is the stuff that we've started after spring break. And what we did, and we actually did a little bit of this before spring break, we looked at magnets. And we put compasses here, and we noted that the magnetic field followed along from the north pole. It emitted from the north pole of the magnet to the south pole of the magnet. It goes out the north into the south because all north-seeking poles are repelled from the north end of the magnet. So the magnet pushes the magnetic field out that way. It has a direction, and they picked one. But what we found was that the strength of the magnetic field is proportional to the number of lines, of magnetic field lines that go through a region of space. So here it's strong, where it's up close to this magnet that was here. But over here, where there are less magnetic field lines, it was much weaker because we didn't have as many lines passing through there. So the concentration of the magnetic field, the flux density, the number of lines per area, is proportional to the magnetic field in Tesla. Now this is going to be important because when we start scraping wires across magnetic fields in the right orientation, it's going to push particles down the wire just like it did before, F equals QVB. But now if we have them move down the wire, we generate current by scraping wires across magnetic fields. And so we introduced the concept of flux. And that's the part we didn't hit hard, but what's happening here is that when you have a magnetic field and it is a flux per unit area, a Tesla, which is a Newton per amp meter, which is a Newton per coulometer per second, can also be thought of as a Weber, named after a guy, per meter squared, a flux per area. And so the flux, we're using the Greek phi for that, is in Webers, or it can be thought of, if you solve this, a Tesla meter squared. We didn't get into that, we don't want to get into that. But when we scrape a wire across the magnetic field, this is part of what Faraday's law is. In that what Faraday's law says is that the voltage induced in a wire when you scrape a wire across the magnetic field is proportional to the rate of the change of the flux. So if we go faster, we get more voltage. If we have a longer wire, we get more voltage. If we have more turns of wire, a bigger number of wires, we get more voltage. If you have a multi-loop wire and each strand of the wire is cutting across the magnetic field, what you're getting is you're getting this battery, this battery, this battery, this battery, and you're adding those voltages in series like having many batteries in a row. And so you get more voltage if you have more turns of wire when you scrape this thing across the magnetic field. And so the voltage, you could say that a volt is a Weber per second, flux per time. It's still an amp ohm, a V equals IR Ohm's law. There's a carryover. We're going to use Ohm's law in these problems. So if we have a voltage, we can go find a current if we know the resistance. Or if we have a current, we can go find the resistance of the wire. We are going to use Ohm's law in this unit as well. It's a bleed over from last unit. So the picture looks something like this. Let me make sure that we can see that on our camera down here. And so you've got a wire that you're scraping across the magnetic field. Just like before, if you scrape the wire parallel to the magnetic field. So you're pushing this wire so that it's going in the direction or in the opposite direction of the magnetic field, no voltage. You have to break across flux. You have to take it and scrape it, and it's only the perpendicular component that is going to create current. So if you go this way, it's only the perpendicular component, the flux you break across, that gives you voltage and or current. So the voltage, since the magnetic flux is the magnetic field strength times the area, the voltage is going to be B times A over T. Bigger area, more voltage. Bigger B field strength, bigger magnetic field strength, more voltage. Go faster, Go faster, so T is shorter, more voltage. Go slower, T goes up, voltage goes down. And so when you take this area, and I've lost my L here, it's going to be length, the length of the wire times the distance of travel. This is the area of the flux that you're breaking across as you scrape this wire across here. It's going to be the length of the wire times the distance it travels per time. Because we're doing this, it's the rate at which you cut across the flux. And when you take distance per time, which we were having troubles with in a couple of classes, basically that's B times length times the rate or the speed that you scrape the wire at. BLV, the voltage induced, is magnetic field strength times length times the speed. And so here's our units. The voltage can be thought of as a Tesla meter squared per second. That's flux per B A per T, BA per T. It's a Newton per amp meter times a meter squared per second, which then becomes a Newton meter per amp second. And if you go back and recall, when we first created and thought about what is voltage, we said, look, it's joules of energy per coulomb to move a charge from one point to another. So a Newton meter is a joule, an amp second is a coulomb. So Tesla meter squared per second, a flux per time, is our same old friend, the voltage. Now, when we did this, we came up with a number of apparati. We said, look, if you take and you scrape a wire across a magnetic field, and you just sit and rotate a wire in a magnetic field, mechanical energy to current and voltage, electrical potential energy, that's called a generator. And so we said, look, if we have this little coil of wire and we're physically scraping or rotating this wire in a magnetic field where you have a north pole and you have a south pole, so you have a magnetic field that's going to the right here. If we have a magnetic field and we physically scrape this wire around and pull it so that it's like we just rotate it with a handle here, and we sit and rotate this, or rotate it this way, as we pull it down here and pull it up there because it's rotating around this point, that velocity through a magnetic field is going to cause a current, and the current's going to run along the wire. If we make this all oriented right, you're going to have a current, and over here you're going up and you're going to have a current going this way. You are going to generate a current. And in fact, this particular device, if you're rotating a wire in a magnetic field, first the current's going this way at 90 degrees when the wire's oriented this direction. It's going 0 because you're going parallel to the magnetic field. And then call this wire A and this wire B, as this wire gets over here and starts coming up this side, the current's going to go in the opposite direction. So what you get out of a coil of wire rotating in a magnetic field is alternating current. And because there's resistance in the wire, you're also going to get an alternating voltage, some voltage that would be in phase with the current. And so you get an alternating voltage pushing back and forth, back and forth, back and forth, but you get energy out. Current, voltage, run your vacuum cleaner stuff, run your clock in your house. You generate electricity. This is called a generator. Now, if instead of mechanically rotating this wire in the magnetic field, we put the current through the coil of wire, so we literally take and we put a current through a coil of wire in a magnetic field, instead of rotating it, we put electricity in, and when we have electricity, if the current's going this way over here, and the other current's going around in a circle, it comes out over here, then what's going to happen is you have a current in a magnetic field. The magnetic field's going this direction, the current's going that direction. We're going to get a force acting on that wire. Now these wires are running parallel to the magnetic field, so they're not going to feel a force going in or out or anything like that. But the current going this direction in the magnetic field is going to feel a force going down over here. So while the wire's on this side, the force is pushing it up, over here down, and it's going to start to rotate, in this case in the opposite direction. And so when you put electrical potential energy, aka current, in, and you get mechanical energy out, because now you've got this thing rotating, and if you can convert that rotational energy into anything, you're doing mechanical work. When you put in electrical potential energy and you get out mechanical energy, that is what we're calling a motor. And a motor is a simple thing like a fan. You just mount blades on this thing, and on a hot day you sit in front of it and it blows air across you and you feel, oh, cool kind of thing as you do that. So a motor is just a simple device that will rotate when you put electricity through the little coils of wire in a magnetic field. The last one is this, and we took a look at, well, first of all, we did look at the concept of a galvanometer. The other question was, what's a galvanometer? So a galvanometer is where you have a coil of wire that's mounted, well, we'll still mount it the same way. Mount a coil of wire in a magnetic field. Here's our magnets. And if you put a current through this, but it doesn't have free rein to keep rotating around, and you mount a needle on this thing, let's put our needle here, and we'll put our current going this direction instead of that other direction. When you put a current through this thing, and you have a magnetic field going this way, and you have a current going that way, it's going to cause this to bend down, this to go up. There is a torque on the wire because you have a force off axis, and it's going to rotate this needle over, and you can calibrate it. So our needle has some calibration on it, and so a galvanometer, and galva has to do with magnetic fields. A galvanometer will measure whatever it is that you calibrate the current to go through here. So it could be your speedometer, it could be a voltmeter, it could be an ammeter, it could be the sound level in your speakers on your amplifier. As it goes, you just make sure that the current happens to be related to the energy coming out of your speakers, and it tells you how loud it is. You can even have a red zone over here so you don't blow your amplifier or blow your speakers and stuff like that. It's like, don't go above that current right there. So a galvanometer is just a coil of wire mounted on in a magnetic field so that it can act like an analog meter. And then the last thing that we did was a transformer. And the way the transformer worked, and we took a magnet, we put it close to the coil of wire. You have two coils of wire. You have a secondary coil. I want to make it blue here. And so you had two coils of wire. When you have an alternating current going into this coil, the magnetic field is first going one direction, and then a portion of a second later, if it's coming out of the wall, 1/60th of a, well, 1/120th of a second later, it's going back the other way. And then back and forth. It alternates. It's got a cycle of 60 hertz. So when it's alternating back and forth, what will happen is the flux is constantly changing. And since delta flux per delta T on a wire is going to induce voltage, you induce a voltage into the secondary coil. Just sitting here by an... Now, if it's constant, if you just put a DC current through here and you put a magnetic field in it, it's just going to sit there because it has to have change in flux per time, not just flux. That will give you a voltage in the secondary, which is equal to not so much the voltage in the primary, because it's the amount of flux. And remember I said if you have like 1, 2, 3, 4 wires here, if N equals 4 over here, you're going to have flux going through those 4 wires. But if you only have 1, 2, 3 or 1, 2 over here, you're going to have less change in flux over here. You're going to have less voltage here. So what ends up happening is the number of turns in the secondary, so the flux is equal to, like voltage is the flux times the number of turns. That's part of the flux. The ratio of the number of turns is the ratio of the voltages that you get out of these things. And this is where we start talking about a step up or a step down transformer. If you have 120 turns here and you have 40 over here, you're going to have a 3-to-1 step down transformer because you're going to get 1/3 the voltage coming out of the secondary that you put into the primary. Why do you need to do that? Well, when you plug your phone in to charge it over here, you don't want it to have 120 volts. So you need to step the voltage down so you don't fry the thing. So many of the devices in your house, we have a step down transformer to take it from 120 down to some lower amount. You may need more voltage. We pulled out that cathode ray tube, the big old tube that shoots electrons. You can't do that with 120 volts. You need more voltage, so you would actually make less turns in the primary and more turns in the secondary. And again, here's where it looks like you're getting magic, because you're like, you put in 120 and you get 600 out. But what goes on with these transformers is this. The power in is equal to the power out. You can't get something for nothing. And so power in equals power out. So when the current in times the voltage in is equal to the current out, or in the secondary times the voltage out in the secondary, when the voltage goes up by a factor of 4, the current has to go down by a factor of 4. When you do that, you have to go 1/4. And so when they talk about step up or step down in these transformers, they're talking about which way does the voltage go. But you still have the same power going in and coming out. This is the back side of worksheet 11 that we have right now. And so as we work these things, take a look at this and work your worksheets, and we'll be taking that test soon.